Have you ever wondered how an application like Twitter works internally? As you imagine, it has a massive amount of people that are using it, and it has huge amounts of daily traffic. But how is such a design engineered? And what components should it have? These are also popular interview questions, and we will tackle them in this video. When answering a system design question, it's beneficial to have a plan of action. First, we need to establish the requirements of the system and define what we want to achieve. In the beginning of the interview, it's critical to ask refining questions in order to clarify the functional needs, the scope of the system, and also the non-functional requirements. Also, the system design interview is particularly open-ended, and there is no such thing as a standard answer. It doesn't matter what specific tool or solution we'll use. What matters is to understand the problem, how we analyze the issues step by step, and how we arrive at the solution. If we want to build a system like Twitter, we would need to provide at least the following core features. Post a new tweet. This can be simple text, links, images, or videos. Then, other users should have options to comment, retweet, like, or share on that tweet. Then, follow or unfollow an account. Then, when a user accesses the homepage, he should receive tweets from the people he's following, ranking in relevancy order. This page is also known as the Newsfeed. Also, a user should be able to search tweets and also see trending topics in his region. There might be other features, like creating an account or getting notifications, but these are common to many applications and are not something specific to Twitter. The interviewer might pick some specific areas, but don't worry, we'll cover most of the topics in this video. For the non-functional requirements, we should expect high availability. Although this is taken for granted these days, it takes a lot of effort to achieve it. But it would make the news if the whole Twitter app would be down for a couple of minutes. Furthermore, the system should be scalable. The Twitter system should be able to cope with the ever-increasing amount of traffic and data. Then, to keep the users happy, we need fast responses from the application. Posting a tweet should be fast, but that wouldn't be so difficult to achieve. However, an interesting problem is when an account with millions of followers makes a post. How should we propagate this tweet to all the followers? Also, how does users immediately receive the most relevant tweets on their newsfeed page? We're going to find these answers in this video. In order to achieve the non-functional requirements, we would need some estimations about the size of the traffic and the size of the data. Depending on what numbers we expect, we'll end up with different architectures. We might ask, why not make an architecture that supports 10 times more than the highest expectation from the start? As we'll see, high-demanding applications tend to require more complex architectures, they're more difficult to build, and of course, resource consumption will be higher as well. So, we need to ask the interviewer for such estimations. For instance, for Twitter, we might expect 100 million daily active users. And let's say that each user adds on average 3 tweets per day. However, we might observe that Twitter is a read-heavy application as opposed to write-heavy. Since read-to-write ratio is very high for Twitter, we should look for optimizing this kind of pattern. Then, for the data usage, we might have the following estimations. The text within a tweet might not be a problem, as the 280 characters allowed for a tweet would fit into 280 bytes. However, these days, most tweets have some kind of media. So, we might start thinking to use different databases for different target data. Cassandra to store the huge amount of tweets, Elasticsearch for the searching functionality, and the blob store to store large binary objects such as images and videos. Now, back to the data estimation, we might consider an average size of 10 kilobytes per tweet, and if we multiply this with the number of tweets per day, we'll get roughly 3 terabytes of data per day. Now, we have a rough idea of what we should expect, but we should further consider a whole year worth of data. Could we store and retrieve that data efficiently from a traditional database? Probably not. What happens in the backend when someone adds a tweet? The tweet would likely be saved to a database, but probably there will be more than just that. There should be a process that distributes this tweet to the timelines of all the followers. We'll call this process Fanout service. Then, it would make sense to have a notification service that would inform users that someone they like have published new content. Since we want to make sure that all three services are involved when posting a tweet, we'll need to have a manager service. As this is related to writing tweets, we'll call it Write API. At a high level, when someone wants to see their Newsfeed page, the following process can happen in the backend. First, the request of the user will be redirected to a service that is responsible for building the newsfeed or the home timeline. First, let's consider what we normally have in the newsfeed page. It will mainly contain tweets posted by users a person follows. There could also be tweets matching a hashtag or a topic or advertising, but we'll keep it simple for now. Therefore, the job of the newsfeed service is to first collect the user IDs of the accounts a person is following. After that, it will need to fetch the tweets made by those user IDs. Then, merge the tweets and finally sort them in order to retrieve the most relevant tweets first. Usually, tweets are ranked based on parameters such as relevance, timestamp, and users' engagement. However, executing all these steps for all the users can become expensive. The queries involved here will be heavy on the database, especially when millions of users are involved, and we can't let the users wait. A cache would definitely help here, but it probably won't be enough. So, it would be great if the newsfeed cache would be already pre-computed. In that case, we would have a separate process to periodically update the cache. We'll see later in the newsfeed deep dive how to build such a push-pull mechanism. In order to store or retrieve data, we need to communicate with the backend services. We do this via the API endpoints. Let's see how we can design those. The two most important APIs would be Feed Publishing API and the Newsfeed Retrieval API. To publish a tweet, an HTTP POST request will be sent to the server. The path could simply be API/feed, but it should contain at least the following parameters: the content, which could be text or media type, and the authentication token used to authenticate the API requests. Based on this, we could also determine the user ID that is writing the tweet. This endpoint could return a boolean, which could tell whether the operation was successful or not. To get the newsfeed page, users can make an HTTP GET request at API/feed, and they should provide at least authentication token. This endpoint would return a list of the tweets that need to be displayed on the newsfeed page for the current user. Finally, we could have the follow or unfollow endpoint. The path can be an HTTP GET on the profile page followed by the action name. Then, we would need to provide the authentication key to identify the user. Now, out of the three components involved in posting a tweet, the most intriguing one is the Fanout service. So, let's take a deeper look at how it works. The goal of this service is to deliver each particular tweet to the users. There are two common ways to achieve this. We can push the tweets to the recipients, or we can prepare the tweets in a nicely form and let them be pulled by the users. In the push model, we can deliver the tweet immediately after the publication to all the home pages of all the users. This model is also called Fanout on write. The advantage here is that the post is pushed immediately to the followers, and therefore the newsfeed is populated in real time. However, if a user has many followers, fetching the followers list and populating the newsfeed for all of them will be a slow and resource-intensive process. As you imagine, this model involves a large number of writes on the database. Moreover, for the inactive users, this approach would be a waste of resources. On the other hand, we can let the users pull the most recent tweets when they load their homepage. This is why this model is called Fanout on load. When using the pull model, the most recent feed is retrieved only when the user makes the request. Therefore, this approach involves only a fraction of write operation on the database, and in this approach, we won't update the newsfeed for the inactive users. However, the obvious downside of this approach is that users won't be able to view recent feeds unless they pull the data from the server, and fetching the newsfeed on demand could be slow. So, what shall we choose? In general, we want to push the feed as fast as possible. However, the push model won't be achievable for all the users. For instance, for famous users that have huge number of followers and that also tweet a lot, it would be a storm of writes to the database for any tweet they post. So, in this case, we let the followers pull the new content on demand to avoid overloading the system. Therefore, we use a kind of a hybrid between the two models, depending on the number of followers a user has. This way, we combine the benefits of the two models. The main job of the Fanout service is to take care of distributing a specific tweet and to do it efficiently. More specifically, it should gather a list of recipients and deliver to them. This looks simple enough without considering the scale and the throughput. Let's see how it would work. First, we need to fetch the followers that a certain user has from somewhere, most probably a database. We don't want to retrieve all possible information related to a follower, but just the ID. We want to read as few bytes as possible for each request. Considering that relationships between people look similar to a network, it would make sense to use a graph database to store the links between users. These two are popular options. This kind of database will help us manage complex relationships and also make friends recommendations. Then, we might ask, should all the followers receive a certain notification? Each user might have certain preferences from whom he wants to receive tweets. Even though a user follows someone, it doesn't mean he actually wants to receive constant feeds from them. Or, on the other hand, a user might want to share a tweet only with specific peoples. So, in order to achieve this filtering, we need to retrieve preference information for each user. And therefore, we'll need to access the database where the users are stored. Again, we extract only what we need. Moreover, since we'll do this operation every time a tweet is posted, which is often, it would make sense to put the user information in a cache for fast access. At this point, we have the Twitter data and the user IDs that need to receive this tweet. Next, to deliver these tweets, we could simply inject these tweets into users' timelines when these are already constructed. This is the push model, so the content is published immediately. However, as we saw, this is feasible only when the numbers of followers someone has is small or medium. If the number of followers is large, then we'll have huge spikes in the number of writes. So, in that case, we let the users pull the new content. But how can we serve the data as fast as possible? Using the latest tweets and the user IDs, we can build a mapping table that we can store in memory. Basically, this is a pre-computed cache that we can use later to populate users' newsfeed whenever they ask for it by accessing the homepage. However, the memory consumption can become very large if we store the entire post objects in the cache. So, we'll store only the tweet ID and the post ID. Also, we already have the tweet information in a dedicated database and we want to keep it in a single place to avoid data duplication. Even so, the size of the cache can become pretty large pretty fast, considering the large number of users multiplied with the large number of tweets. Thus, it would make sense to set a configurable limit for the cache. Most users are interested in the latest, most relevant content. The common usage pattern of a person is to scroll to a couple of tens of tweets. So, if we store just that, we'll have a high hit rate for the cache. Usually, the benefit of a cache system is given by the hit rate percentage. The higher, the better. We'll see how this cache can be used in the next section. Next, let's see how we can build a newsfeed in an efficient manner considering the scale of Twitter. We already have a pre-computed cache where we stored fresh tweets IDs together with the IDs of the users that need to receive the updates. However, in that cache, we only have the tweet ID and the post ID. So, we need to inflate the tweets. There is a lot of information in a tweet. We have the content, information about the author, comments, number of likes, date of publication, and so on. First, we can gather the information about the author, such as username, profile picture, and so on, from the database using the user ID. Furthermore, the information related to a specific author will be retrieved frequently after the tweet is published, especially if the author is famous. So, we could put a cache in front of the database for fast access. The same rehydration process would happen for the tweet data. As you might guess, we should also cache this data as well, especially for the hot tweets. Moreover, the tweet content can have images or videos. In that case, it makes sense to also add a content delivery network. Then, the user will connect to the closest CDN server in his region to retrieve static images or videos. This will increase content availability and redundancy while reducing the bandwidth cost. Finally, with all the fresh tweets fully hydrated from all the people a person follows, also fully hydrated, we could build a JSON file that would finally be sent back to the client for rendering. How can we provide a search functionality while considering the amount of tweets that need to be indexed and the amount of search requests that are being made by all the users? A traditional relational database would probably not be performant enough considering the size of the data and the fact that searching would be done mostly on text rather than keys. So, a good candidate for such a use case would be a search engine like Elasticsearch or Apache Solr. These search engines could index, search, and analyze huge amounts of data quickly, possibly in real time, and give results back within milliseconds. But what's the secret sauce behind these databases? They both are using an inverted full text index. In simple terms, this means that whenever a tweet is posted, the tweet will be passed through a chain of tokenizers and analyzers to be processed. After the text processing is done, we'll add these words in a big distributed index. This index is basically a mapping table where each word will have references to the tweets that contain that particular word. Since the data will be laid out in the exact form necessary for searching, it will be extremely fast. Suppose the user is searching for the word Twitter, then the engine will go through the table, it will immediately find the word Twitter, and then it will get all the references of the tweets in that system. Additionally, the results that are returned can be ranked based on relevance, engagement, and freshness. Furthermore, this index will be distributed across multiple nodes. This means that we could scale out as the data continues to expand. Next, we'll see how the functionality of trending topics can be built on top of the searching feature. A topic becomes a trend when people start searching for it. Therefore, using the search service, we could gather statistics about the most frequently searched queries, hashtags, and topics in the past day, week, or month. Then, we can update the statistics every hour by using some sort of scheduling mechanism. Additionally, we can customize the trending results based on location and user interests. Because there are so many users and tweets, it's impossible to keep all the data on a single server. First, it wouldn't fit. Second, it would be slow when retrieving the data. So, to scale out our database, we would need to split the data into partitions and distribute them on multiple nodes. This kind of partitioning is also known as sharding. The partitioning can be done using different classic strategies such as the following. These strategies are pretty good when it comes to data distribution. However, these methods are disappointing when it comes to adding or removing a node from the cluster. This is also the case when a node breaks down. In these situations, a full redistribution of the data would be necessary, and as you imagine, this would be very expensive. A better approach would be to use consistent hashing because it limits the resharding area only to a fraction of the whole data. We have a separate video on this topic. When we build the newsfeed page, we should rank the tweets based on how relevant they are to a specific user. The more relevant the tweets are, the more time it would be spent on the application, which is what any social application wants. Here, we can take into consideration the user interaction with different topics or different accounts. For instance, if a user liked a tweet, then we'll assign a certain relevance weight, or if he commented on that tweet, we might add a higher weight. But how can we collect the data about the user activity in an efficient way? Here, we can use a queue, such as Apache Kafka, to publish all user interaction with the application as a queue event. Then, we can process these events and run different jobs to build different analytics. Here we can use Apache Spark, which is an open source analytics engine for large-scale data processing. Every company has its unique requirements and constraints, and we should always find a way to fit those requirements. As always, there is no standard way to design a system. This is also the case in the interview. So, what's important in a system design interview is to understand the problem, to analyze the issues step by step, and to discuss the benefits and trade-offs of each design.